Hi students, good morning all of you. Hope you are all doing good. Welcome to lecture 42 in this course. At present we are discussing definite integrals unit, and our today's topic is area under the curves. In this lecture we will be discussing some results for finding area under the curve, and we will solve some problems on finding areas using definite integrals. Now we will be discussing the applications of definite integrals, namely finding area under the curves. Now, using definite integrals, how to find out the area. So I will be discussing for 6 to 7 results to find area under the curves using definite integrals. Here is the first result. Here is the statement of the first result. Let if f is a continuous function from closed interval ab to closed 0 to open infinity, then area A of the region bounded by the curve y is equal to f of x comma x-axis and the lines x is equal to a and x is equal to b is given by. Now let me explain what is being given in the statement graphically. So I have considered this example. So here is my f of x, here is my a comma b, and in the hypothesis it is mentioned f of x must be non-negative. That means f of x is greater than or equal to 0. That means graphically, okay, the graph of f of x must lie above x-axis. Anyway, exactly it fits into this, right? Now then the area A of the region bounded by the curve y is equal to f of x. Okay, this portion of the curve is y is equal to f of x, and this is the line x is equal to b, and this is the line x is equal to a, and this is the line, this is x-axis. Now area bounded by these four curves, namely y is equal to f of x and x-axis, x is equal to a and x is equal to b, is given by area A is equal to integral a to b f of x dx. That means if you integrate the function f of x from in the interval a to b, then we get the area under the curve bounded by the function y is equal to f of x, x-axis, x is equal to a and x is equal to b. Remember, you can get area by integrating the function only if the function is non-negative. Okay, I hope you have understood the result. Let me discuss the second result now. Here is the statement of the second result. Let f is a function, a continuous function from closed interval ab to minus infinity to 0. Then area A of the region bounded by the curve y is equal to f of x, x-axis, and the lines x is equal to a and x is equal to b. So let me explain the statement of the theorem with the help of a graph. So what is being given in the statement? F of x is negative. That means f of x will be negative. Graphically, what does it mean? The graph lies below the x-axis. The graph lies, you can see that the graph of f of x lies below x-axis. Okay, so here is my point x is equal to a, and here is my point x is equal to b, and here is my graph y is equal to f of x, and this is your x-axis. Okay, so we have to find out the shaded region as shown in the figure. Now, how to apply the area of the shaded region? Now, I would like to apply result 1 to find out this area. How do I apply the previous result? To apply the previous result, I need my function to be positive. But of course, in the given function, it is given as negative. So how do I make it positive? By multiplying minus sign. That means now I will consider the function minus f of x, and minus f of x is a graphical transformation, and you know that if f of x is negative, then minus f of x will be positive, and the sketch of that graph will be like this. So if I consider this as my area A1 and this as my area A2, literally since it is a reflection, A1 is equal to A2. Now finding area A2 is nothing but finding area A1. Okay. Now how do I find area A2 using the previous result? Okay. So it is anyway, these two will not be changing. This is A comma B. So this is A to B. Now here the function is y is equal to minus f of x. So I will integrate minus f of x dx. So a1 is equal to a2 is equal to minus integral a to b f of x dx is the formula. So here is the formula for finding area under the curve in the given scenario. Hope you have understood the statement of the theorem both mathematically and graphically also. Let me discuss the next result. Here is the statement of the next result. Let f be a continuous function from closed interval ab to r such that f of x is positive for all x belongs to closed interval a to c, and f of x is negative on the interval c to b, where c is a point in between a and b. Then the area A of the region bounded by the curves y is equal to f of x, comma x-axis, and the lines x is equal to a and x is equal to b. This is the area of the region that we have to find out. Okay, let me explain the hypothesis with the help of a diagram. So here this is the scenario here. So these are the line, this is a line x is equal to a, and this is let me write it as a, and this is my point b, and this is the point c. This is the line x is equal to a, and this is x is equal to b, and this is my x-axis. This is my x-axis. Okay. Now in the hypothesis it is given that f of x is greater than or equal to 0 over the interval a to c. So in the interval a to c, f of x is positive, and you can from the graph you can see the graph of f of x is greater than lies above the x-axis. So f of x is positive here, and f of x is negative means in the interval c to b the graph of f of x lies below x-axis. So now the area bounded by these four curves, namely y is equal to f of x, x-axis, and the lines x is equal to a and x is equal to b. So the area, the required area is shaded here. So that the entire area has been split into two parts, namely a1 and a2. So the entire area a is equal to a1 plus a2. Now how do I find out a1? So a1, if I look at a1, so in the interval a to c the function f is non-negative, that is positive, non-negative. So I can find out this area a1 using result 1. That means a to c f of x dx. Using the first result I can find out this area. Now how do I find out area a2? Now here the function f lies below the x-axis, or the function is negative in the interval c to b. Here I can apply the second result to find out area a2. So what does the second result says? This area can be found out using this integral c to b minus f of x dx. So graphically what you need to do is this portion of the graph needs to be reflected and then find out the area. So here is the reflection, that means this is area a1, and upon reflection this is my point c, and this is a, and this is b, and this is f, and this is minus f. Okay, this is the area a2. Okay, so the total finding total area a is given by integral a to c f of x dx plus integral c to be minus f of x dx. Hope you have understood this result mathematically as well as graphically. Let me discuss the next result. Here is the statement of the next result. Let f comma g are two continuous functions defined on the closed interval ab, and f of x is less than or equal to g of x on the closed interval ab. Then the area A of the region bounded by the curves y is equal to f of x, y is equal to g of x, and the lines x is equal to A and x is equal to B is given by. Before having a look at the formula, let me explain the statement of the result, the statement with the help of a graph. Here are two curves, namely y is equal to x square and y is equal to x cube. This is the example that I have taken. So my f of x here is x square and g of x is equal to x cube. Okay, and my a is 2 and b is 3. So these are the lines x is equal to a, and this is the line x is equal to b, and this is f of x and this is g of x. See, graphically, what does it mean f of x less than or equal to g of x? That means the graph of g of x always lies above the graph of f of x. You can see that the graph of g of x lies above the graph of f of x here. Now we have to find out the area of this shaded region. Okay, now let me denote the area of the shaded region by a1, and this empty region, this is a2. Let me write my f of x here. This is my f of x. Okay, so now let me extend the straight line x is equal to a and x is equal to b. Now you can see that integral a to b g of x dx is equal to what? Integral g of x dx is equal to the sum of these two area. This is by result 1. Okay, because this area and x-axis, this is the x-axis. Okay, so we will be getting a1 plus a2. Now let me ask one more question. Integral a to b f of x dx would be what? Now that means area under this curve f of x, so this curve is going to be a2. Now I require a1. So what is a1 here? So a1 is equal to, so a1 is equal to integral a to b g of x dx minus a2. Okay, now area a1 is equal to what? Area a1 is equal to integral a to b g of x dx minus integral a to b, because a2 is what? a2 is equal to integral f of x dx. So this would be the formula. Okay, there is one more scenario. Of course, here I have assumed, in this example I have assumed both f comma g, both f of x comma g of x are positive. Now there is one more case where f of x comma g of x both are negative and still have this relation, f of x is less than or equal to g of x. Let me show you that example also. Here I am considering the two curves, namely y is equal to minus x square and y is equal to minus x cube. So in this scenario I take my g of x. G of x is always above, so this is minus x square, and f of x is equal to minus x cube. And graphically you can see the graph of minus x square lies above the graph of minus x cube. So g of x is greater than or equal to f of x. Of course in this region only I am taking. Okay, now as we did here, we can do the same scenario. We can find out the area in the similar way. Now we have to find out the area of this shaded region. So how do I go about this? Okay, now I have to find out this area. If I want to find out this complete area of the shaded region plus the region shaded with the blue color lines is given by minus x cube minus g of x whole cube, that is g of x whole cube, minus integral g of x whole cube, that is a to b dx it would be. Let me write it here. So that is given by the area a1 plus a2. So this is a1 and this is a2. So area a1 plus a2 is equal to what? Integral minus g of x dx. Sorry, I think area is given by, so this is my f of x and this is my g of x, right? So this would be integral minus f of x dx, a to b dx. And what about this area a2? A2 is given by a to b minus g of x dx. See, I can write these results with the help of result 2. I am using result 2 in finding out these things. Now I require the only shaded region a2, so a1. So a1 is equal to, so a1 is equal to, let me write it here. So a1 is equal to integral minus f of x dx a to b minus a2. So that is equal to integral a to b minus f of x dx minus a to b minus g of x dx. So that is going to be area a1 is equal to integral g of x minus f of x dx over the interval a to b. Okay, so even in this case also we have got the same formula, g of x dx minus f of x dx. Even in this case also we have got the same formula. Now we have one more situation wherein f of x, g of x is positive and f of x is negative. So this is the case where g of x is positive and f of x is negative. Now in this case, this is this is here we have to find out this shaded region. So this shaded region can be divided into two parts, namely a1 plus a2 here. So total area A is equal to what? a1 plus a2. Total area is equal to a1 plus a2. So area of a1 can be find out easily. This area a1 is given by integral a to b g of x dx. This is by result 1. This area a2 can be given by result 2, that is integral a to b, so minus f of x dx. Okay, so in whatever the case that we take, the formula for finding the required region is integral a to b g of x dx minus integral a to b f of x dx. Both put together we get this result. Okay, integral area is equal to g of x dx, integral a to b g of x dx minus integral a to b f of x dx. Combinedly we get integral a to b g of x minus f of x dx. Hope you have understood this result both mathematically as well as graphically. Let me discuss the next result. Here is the statement of the next result. Let f of x comma g of x be two real valued continuous functions on closed interval ab, and c be a point in the interval ab such that f of x less than g of x on the interval closed a to open c, and g of x is less than f of x on the interval open c to closed b, and with f of c is equal to g of c, then the area of the region bounded by the curves y is equal to f of x and y is equal to g of x under the lines x is equal to a and x is equal to b is given by. Before having a look at the formula, let me explain the result with the help of an example. I will show this result graphically. See, here I am considering the two graphs, namely f of x and g of x. Let me write what are my a and what is my b. So this is my a and this is my b and this is my c actually. So I have considered the two curves here, sin x and cos x here. Okay, this is for the example sake, this will be pi by 4. At exactly pi by 4 these two gets intersected. See, in the hypothesis it is given that f of c is equal to g of c. That means the two curves intersect at c. So this is the meaning of f of c is equal to g of c. The two curves intersect. Okay. Now in this interval a to c, f of x is less than g of x. That means this is the curve g of x and this is the curve f of x. Now after c, the g of x curve will go below and here the after c f of x will be above. Now in this interval c to b, f of x dominates g of x. Dominates means f of x is greater than g of x. Graphically it means the graph of f of x lies above the graph of g of x in this interval. In this interval the graph of g of x lies above the graph of f of x. Okay. Now what is that you have to do? You have to find out the area of the region bounded by the two curves y is equal to f of x and y is equal to g of x and the two straight lines x is equal to a and x is equal to b. So this is the straight line x is equal to a and this is the straight line x is equal to b. So this is the area of the region that we need to find out. So the entire area is splitted into two parts, namely a1 and a2. So a is equal to, let me write a is equal to a1 plus a2. Okay. Now how do I find out a1? So how do I find out a1? So a1 is equal to, this is the region that we need to find out. Okay. Now by result 4, I can write this area as integral a to c g of x minus f of x into dx. Okay, because g of x lies above the graph of f of x. So this area of the region a1 is given by integral a to c g of x minus f of x. Now area a2. So how do I find area a2? So with the help of result 4, again this will be integral c to b. This is going to be f of x minus g of x dx. Now I require the entire area. Entire area A is equal to a1 plus a2. So the formula for finding the entire area is integral a to c g of x minus f of x dx, and that of a2 is integral f of x minus g of x dx c to b. So the formula for finding the shaded region is given by integral a to c g of x minus f of x dx plus integral c to b f of x minus g of x dx. So this result we have derived using result 4. Okay, I hope you have understood this result both mathematically as well as graphically. Let me discuss the next result. Here is the statement of result. let f comma g are two continuous functions defined on the closed interval ab to r. Suppose that there exists points x1 comma x2 in the open interval ab with x1 less than x2 such that f of x1 is equal to g of x1 and f of x2 is equal to g of x2 and f of x greater than or equal to g of x for all x belongs to x1 comma x2, that is f of x is greater than or equal to g of x in the open interval x1 comma x2. Then the area A of the region bounded by the curves y is equal to f of x comma y is equal to g of x and the lines x is equal to x1 and x is equal to x2 is given by. So before having a look at the formula, let me explain the statement graphically. So this is the graph that I would like to show for this particular statement. So this is the curve g of x and this is the curve f of x. So this is my f of x and this is my g of x, and you can see the formulas for the curve. Y is equal to 1 plus x square is your g of x and y is equal to 2 minus x square is my f of x. Of course this is my a and this is my b, and this is my x1 and this is your x2. So this is the line x is equal to x1 and this is the line x is equal to x2. So this is f of x, and you can see that f of in the interval x1 comma x2 f of x greater than or equal to g of x. That means the graph of f of x lies above the graph of g of x in the interval x1 to x2. Anyway, that condition is met, and further it is given that f of x1 is equal to g of x1, f of x2 is equal to g of x2. That means at this point x1 comma x2 both the curves intersect. Okay, now I need to find out this shaded region. This is the shaded region. This is the required region that we need to find out here. Anyway, now how do I find out this area? So let me denote the shaded region by A2 and this complete region, okay, bounded by the lines x is equal to x1. That means this region I am talking about. Okay, this is let me denote this by A2. So I need to find out A1. So this is what I need to find out. Okay, now using result 1, okay, this integral x1 to x2, integral x1 to x2 f of x dx is equal to what? It is given by a1 plus a2. As f is a non-negative function, so integral f x dx x1 to x2 is equal to a1 plus a2. Now what does this integral represent? x1 to x2 g of x dx. G of x dx means this entire area a2. Now what do you require? a1. So a1 is equal to what? Integral x1 to x2 f of x dx minus a2. What is that a2? So integral x1 to x2 f of x dx minus integral x1 to x2. This is g of x dx. So the formula for finding the required area is given by a is equal to integral x1 to x2 g of x minus f of x. Sorry, I think here it should be f of x minus g of x dx. Hope you have understood the result both mathematically as well as graphically. Let us discuss some problems based on the results which we have proved so far. Here is the problem. Find the area of the region enclosed by y is equal to x cube plus 3 comma y is equal to 0, that means x-axis, x is equal to minus 1 comma x is equal to 2. So if you draw all the 4 curves here, this is how it looks like. Okay, now this is the straight line x is equal to 2 and this is the straight line, x is equal to minus 1 and this is the graph of y is equal to x cube plus 3, and anyway it is easy to draw. Okay, now we have to find out the area of the region bounded by the curves x is equal to minus 1, x is equal to 2 and y is equal to 0 means x-axis. Okay, now this is the region that we have to find out. Okay, so this is the area of the region that we need to find out here. So how do we go about this? Let us do that. Let us find out the area. Solution. So area of the, now we know that the graph y is equal to x cube plus 3, from the graph it is above the x-axis, so it is positive, we can apply result 1. So this is equal to minus 1 to 2 x cube plus 3 dx. Now upon integrating it, what do we get? It is x to the power 4 by 4 plus 3x in the interval minus 1 to 2. Now we apply the upper limit and lower limit, so it is 1 by 4 into 2 power 4 minus 1 whole to the power 4 plus 3 into 2 minus of minus 1. So that is equal to 1 by 4 into 2 power 4 is 16 minus 1 plus 3 into 2 plus 1 is 3. So this is equal to 15 by 4. This is 9. So it is 15 plus 36 by 4. That is equal to 51 by 4. So area of the required region, is equal to 51 by 4 square units. Let me solve the next problem. Here is our next problem. Find the area of the region enclosed by the curves y is equal to e power x, y is equal to x, x is equal to 0 and x is equal to 1. If you draw all these 4 curves, this is how the graph looks like. This is the graph of y is equal to e to the power x. This is the graph of y is equal to x. And this is the line x is equal to 1, x is equal to 0 means y-axis. So we have to find out the area of the region bounded by these 4 curves. This is the region, required region. So you can see this is the required region that we need to find out. Okay, let me show you the shaded region here. So this yellow colored region is the required region. Let us find out that area. Solution. Area A is equal to integral. So integral, the limits are from 0 to 1. Okay, so it is from 0 to 1. The upper curve is, here we are applying result 3. The upper curve is result 4. Upper curve is e power x minus the lower curve is x. So e power x minus x into dx. So that is equal to integral e to the power x is what? E power x minus integral x is x square by 2. So I have to substitute the limits 0 to 1 here. So if I substitute the upper limit, it is e power 1 minus 1 square by 2. or I can evaluate like this. So for the function e power x, I'll substitute the upper limit as well as the lower limit. So e power 1 minus e power 0 minus 1 by 2 into 1 square minus 0 square. So that is e minus 1 minus 1 by 2. So it is e minus 3 by 2. So the area of the required region is e minus 3 by 2 square units. Let us solve next problem. Here is our next problem. Find the area enclosed by the curves y is equal to sin x, y is equal to cos x, x is equal to 0 and x is equal to pi by 2. If we draw the four curves, this is how the graph looks like. Okay. Now this is the orange color curve is the sin x curve. You can see it starts from 0. Okay, at 0 it is taking 0, and the magenta color curve or the pink color curve is y is equal to cos x, and this is the graph of x is equal to pi by 2, and this is your x is equal to 0. X is equal to 0 means y axis. X is equal to 0 means the y axis. So we have to find out which area. So I have to identify the regions where it is enclosed by these curves. So you can see this region, it is enclosed by cos, and this is enclosed by sin, and this is y axis. So this is one region that we would like to find out, and this is the line x is equal to pi by 2, and this is bounded by sin x, and this is bounded by cos x. So this is one more region that we need to find out. Here we are applying a result 5 to find out the required region. So let me show you the shaded region. Yeah, this is the green color part, this is A1, and this is A2, yellow color part. So the required region A is equal to A1 plus A2. So how will you find out A1? Integral. So at this point, so the sin x curve and cos x curve intersects in the interval 0 to pi by 2 at pi by 4. So this is pi by 4. So at pi by 4 I have to separate the integral. So that is 0 to pi by 4. The upper curve in this region is cos x, and the lower curve in this region is sin x dx, plus integral pi by 4 to pi by 2. Here in this interval the upper curve is sin x and the lower curve is cos x dx. So this is how I have to find out the integral. Now integration cos x is what? Sin x, minus integration cos x is minus of cos x. Now I have to evaluate at the limits 0 comma pi by 4. Now integration sin x is minus cos x, integration cos x is sin x. So it is to be evaluated between pi by 4 and pi by 2. Now this is equal to sin x plus cos x, 0 to pi by 4, minus this is cos x plus sin x, this is pi by 4 to pi by 2. So area is equal to, so first I'll apply the upper limit as well as lower limit. It is sin pi by 4 minus sin 0 plus cos pi by 4 minus cos 0. So minus, this is cos pi by 2 minus cos pi by 4 plus sin pi by 2 minus sin pi by 4. Yeah. Now I'll write down these values. Sin pi by 4 value is 1 by root 2 minus 0 plus cos pi by 4 value is 1 by root 2 minus 1. Okay, so this is one set of values, and this is cos pi by 2 is 0 minus cos pi by 4 is 1 by root 2 plus sin pi by 2 is 1 minus sin pi by 4 is 1 by root 2. So this is equal to 2 by root 2 minus 1, 2 by root 2 minus 1 minus, what is this value? It is minus 1 by root 2 minus 1 by root 2. It is 1 minus 2 by root 2. So that is equal to, this is root 2 minus 1 plus root 2 minus 1. So that is equal to 2 into root 2 minus 1. So the area of the required region is given by 2 into, it is 2 into root 2 minus 1 square units. Hope you have understood this problem. Here exactly we are applying the fifth result. Okay, let us solve one more problem here. Here is our next problem. Find the area of the region enclosed by y is equal to cos x and y is equal to sin 2x, x is equal to 0 and x is equal to pi by 2. Now if you plot these four curves on the coordinate axis, this is how it looks like. So this magenta color curve is the sin 2x. Of course this graph is plotted, this is cos x and sin 2x anyway. Okay, the magenta color curve is the sin 2x and the orange color curve is the cos x. Okay, and x is equal to pi by 2. Both these curves meet at x is equal to pi by 2. And this is 0. X is equal to 0 means this is y-axis. So this is y-axis. Okay. Now we need to find out the area of the region bounded by these four curves, namely cos x and sin 2x. See, if you look at this curve cos x, this acts as a boundary, and the sin 2x acts as a boundary, and this is the y-axis. So this is area A1, and if you come at this in this region, so this is going to be enclosed by sin 2x curve and cos x curve, and this is x is equal to pi by 2. Okay, so this is the required region A2. So let me show you the shaded region. So this yellow color region and the green colored region is the required area that we need to find out. Anyway, again it is a problem based on result 5, and this point of intersection we need to find out. How do we find out the point of intersection? I have to solve this equation cos x. We have to solve this equation cos x is equal to sin 2x. So this can be written as, let me write it as sin 2x is equal to cos x. So this is 2 sin x into cos x minus cos x. So cos x, if I take common, then this becomes 2 into sin x minus 1 is equal to 0. So the solution is cos x is equal to 0 or sin x is equal to 1 by 2. So this is cos x is equal to 0 implies x is equal to pi by 2, and sin x is equal to 0 implies x is equal to pi by 6. So the point of intersection here is pi by 6. Okay, now we have to apply result 5. Solution here. The required area A is equal to A1 plus A2. What is that area A1? Area A1 is the yellow shaded region, and the area A2 is the green colored shaded region, shaded in the green color. So it is integral 0 to pi by 6. Here in this region, the upper curve is cos x minus the lower curve is sin 2x dx, plus the second integral is pi by 6 to pi by 2. Here the upper curve is sin 2x minus the lower curve is cos x dx. Now let us compute this integral. Integration cos x is sin x minus integration sin 2x is minus cos 2x divided by 2, plus, of course, this integration is completed. This is 0 to pi by 6. Now let us come back. Let us go to the second integral. In the second integral, it is sin 2x. Integral sin 2x is minus cos 2x by 2 minus integral cos x is sin x. So this is the upper limit and lower limit, and this is upper limit. So the integration part is done. Yes, let me get this point. I think there is a problem with the cursor here. Yes, now I have got the cursor. Yes, that is equal to sin x plus cos 2x by 2, 0 to pi by 6, minus this is cos 2x by 2 plus sin x. The limits are pi by 6 to pi by 2. Okay, now let me compute the limits. So sine function, it is sine pi by 6 minus sine 0. This is one function, plus 1 by 2 into cos 2 pi by 6, cos 2 pi by 6 minus cos 0, minus half into cos 2 pi by 2 minus cos 2 pi by 6 plus sin pi by 2 minus sin pi by 6. Yeah, so this is equal to, there is a problem with the cursor. Yeah, so this value is equal to sin pi by 6 value is 1 by 2 minus 0 plus 1 by 2 into cos 2 pi by 6, that is cos 30. Cos 30 value is 1 by 2 minus 1, minus 1 by 2 into cos 2 pi by 2, that is cos pi value is minus 1, minus cos 2 pi by 6 is cos pi by 3, that is 1 by 2 plus sin pi by 2 value is 1 minus sin pi by 6 value is 1 by 2. Now let me compute this value. 1 by 2 plus 1 by 2 minus 1 is minus 1 by 2, so this becomes minus 1 by 4 minus, so this is 1 by 2 minus 3 by 2, so this becomes minus 3 by 4 plus 1 by 2. So 1 by 2 minus 1 by 4 is 1 by 4 minus 3 by 4 plus half is minus 1 by 4. So that is equal to 1 by 4 plus 1 by 4, that is equal to 1 by 2. So this is equal to half is equal to 0.5 square units. This is the area of the shaded region. Hope you have understood this problem.